Welcome to this video. My name is Mark Scythian. The date today is June 24th, 2024. This video is going to focus on air conditioning and refrigeration systems, particularly the vapor compression cycle, or what most know as the refrigerant air conditioning systems. So before we get into the details of the diagram and its operation cycle, we need to get familiar with the components of a typical air conditioning or refrigeration system. So we start with the condenser, which is located immediately after the output of the compressor. The condenser is a type of heat exchanger that discharges high pressure refrigerant heat while maintaining high pressure refrigerant vapor. So what happens to the refrigerant as it undergoes compression by the compressor is that it will start to convert from a vapor into a partial liquid and then eventually into a full liquid. So when we introduce compression into the gaseous refrigerant, it will incur liquefaction or be made into a liquid while its temperature increases. So our heat exchanger is just a very good thermal conducting structure which allows heat transfer through that structure while not disturbing the increased pressure. So the first heat exchanger, the condenser, its function is to reject heat. Next, we have the evaporator. This is another type of heat exchanger that absorbs or removes heat, thus inducing low temperature ambient airflow and low temperature and low pressure refrigerant. So that's upstream past the receiver dryer, and by the time we reach the evaporator, we then have an expansion valve, which we'll cover in a moment, but we have ultimately the absorption of heat. So now cooling cannot occur since energy is conserved. Only heat removal occurs as higher temperature migrates to lower temperature, not the other way around. So energy of high value naturally migrates to energies of low value. So this is a application of the first and second laws of thermodynamics. The first law is conservation of energy, and the second law is entropy. So the concept of conserving energy is that we cannot create or destroy energy. We can only change its form. Energy itself is the capacity to do physical work. So there's many different forms of energy, such as mechanical energy, electrical energy, thermal energy, luminous energy like light, and acoustical energy like sound. So everything is converting from one type of energy to another. Case in point, if we had a certain fuel or hydrocarbon and we compressed, vaporized it, ignited the fuel air charge, extracted thermal energy from that chemical potential energy, we then can induce a specific pressure spike onto a thermal structure like a piston or turbine, thus converting it now into mechanical power. And so in this case, we are adding mechanical power to then induce pressure into the refrigerant to then ultimately remove heat. If we reverse this process, it would be similar to an internal combustion engine where we add heat in the form of fuel combustion to then induce mechanical power. So we're adding mechanical power to remove heat in air conditioning systems. With internal combustion thermodynamics, we are adding heat to then incur mechanical power. So it is the conservation of energy and the natural order of higher energy states migrating to lower energy states. So that's the first law of thermodynamics, conserving energy, and the concept of efficiency losses, of course, but we're not doing anything to energy except converting it with these devices, these machines, and then during that process we then have diminishing returns and efficiency losses. So that is falling under the second law of thermodynamics, the concept of entropy. So then we move on to the expansion valve. Okay, so if we look at the geometry and the dimensions of the expansion valve, it is a converging, diverging type of nozzle. So initially it is a convergent nozzle, so the higher pressure is decreasing into higher velocity. So in this case, the expansion valve decreases the pressure of the refrigerant, thus converting it from its liquid state back into a gas. So the expansion valve decreases refrigerant pressure and refrigerant temperature, changing refrigerant state from mostly a liquid to mostly a gas. So next we have the compressor. Obviously this is an electrically driven compressor, electric motor, then driving the mechanical compressor. So the compressor's function is to increase the temperature and pressure of the refrigerant from a vapor or gas to a liquid, and then the refrigerant is a substance that easily changes its state from a gas to a liquid or from a liquid to a gas under minimal compression and expansion, having a low temperature boiling point. So refrigerant in an air conditioning system, when it is turned off, is within the refrigerant reservoir as a standing gas. But when you turn on the air conditioner and the compressor kicks in, it will then pressurize the refrigerant into mostly still a gas but partially a liquid at its start point, discharging out of the compressor. So the typical refrigerants are R12, R12C, and in aviation systems, the air conditioning systems are, at least on airline transport, is R134A refrigerant, also known as trifluoroethane, and its commercially traded name is Arcalone or halocarbon. So that type of refrigerant is common in airline transport, air conditioning systems, relying on the vapor compression cycle. And so as the refrigerant flows farther away downstream, away from the condenser, from heat rejection to the evaporator for heat absorption, it has then reached its full liquid state. And the liquefaction of the gaseous refrigerant reaches then a very low temperature, minus 130 degrees below 0 Fahrenheit, and that would be its boiling point. So we have to look at the concept of states of matter and freezing and or boiling point. So we are inducing actually liquefaction while inducing a boil at a relatively low temperature from the ambient atmospheric temperature, so minus 130. And initially, a long time ago, when vapor compression cycle was experimented upon before air conditioning was commercialized, solvents or actually combustible gases were the primary choice, such as propane. And we see that when we compress gaseous propane, it liquefies at a very cold temperature, about minus 40 or below, but while reaching a temperature above minus 40 below 0 Fahrenheit, it will then vaporize into a gas. So there are some shared and not so similar properties of liquefaction of a gas inducing a boiling point, but the concept of heat absorption, heat rejection was then quickly noticed, and of course it all started out with Freon and the chlorofluoro CFCs, the chlorides and fluorides that are involved in the Freon molecular chains was then deemed to be a disassociator of oxygen 3 or the ozone layer. So that eventually the R12, R12C, and R134 refrigerants were replaced with bromine-based fluoroethane chain. So it's just trifluoroethane, but we have a bromide chain, the exact opposite polarity of the iodine electron spectrum in the mass spectroanalysis. So this became the inert yet effective refrigerants. And why I'm touching upon the refrigerant a little bit more is that you're probably studying for an air conditioning exam, and then they're starting to get a little bit more into the base chemical structures, at least essential atoms. And so in this case, we're dealing with a bromide central atom, but then it is trifluorine and ethane chain configuration. So that is then renamed as trifluoroethane. So pay attention to the fluorine substrate and the bromide central atom. It's very important because there are a lot of students that are very astute at air conditioning and thermodynamics, and there's just a little bit of physical chemistry, at least in nomenclature. So keep that in mind. It's kind of important. Your test scores will go up when you keep a little eye on what that central atom is. And if you need to just look up the structure on Google and go to images and look at the molecular geometry, it might be an easier way to remember those differentials and the central atom versus the substrate. Okay, so now we'll go into the details, the actual technical process. You turn the AHC on, compressor kicks in, it starts to pressurize the refrigerant vapor, moves out of the compressor discharge, starts to partially liquefy, and then we're inducing a temperature surge comparatively from its start, non-energized, non-pressurized state. And so the material of the first heat exchanger, the condenser, is quickly transferring that heat overboard while not disturbing the actual physical pressure of the refrigerant. And so then the refrigerant flows away while having its temperature decreased or at least stabilized while its pressure is constant. And so in this point here with the surrounding environment, it's actually difficult to find a perfectly 0% relative humidity environment. Even many deserts or dry areas have some humidity. So in this process, that rapid heat transfer while maintenance of the constant or maintaining a constant pressure will quickly start to create a temperature differential, which wants to precipitate the standing humidity in the air, and you're quickly going to get condensation at this point. So we have a device called a receiver dryer, also known as a liquid receiver dehydrator, but they're usually known as RDs, receiver dryers. Receiver dryer is very apt towards absorbing moisture, but essentially it is a dehumidifier. It's a dehumidifying device. We'll just put it like that. And so it quickly removes that condensation, and some better or more sophisticated designs will actually have a vapor revaporization system. So instead of condensation dripping out, it'll be evaporated. So it's not as obvious, and it's easy to contain these within households if it happened to be an internal type of air conditioning system or even refrigeration systems. but generally you have a liquid condensation port, and it's still kind of common with cars. You'll still see some water dripping out. So that's happening through this RD. Okay, so now we have high pressure liquid, or mostly liquid, upstream away from the RD, all the way to the expansion valve. So now it's reached the expansion valve, its pressure is dropped into velocity based on the expansion valve's geometry. And you see that what happens when we drop the pressure, we're going to return this refrigerant back into a gaseous state, but then there is a rapid differential between temperature and pressure. So the system's heat discharge and the ambient heat must absorb into that differential. So the second heat exchanger is an inverse function heat exchanger, which then takes away all the heat. So in other words, it creates such a low energy state that the higher energy, higher temperature must flow into it. And so it's a heat absorber. And in the process with the blower fan, all that's left is a substantial drop in temperature. So that's the cold air that is delivered. Thereafter, the refrigerant continues to flow, and it starts to revert from a liquid more into a gas, partially liquid, partially gas. And by the time it is almost back to the return state of the compressor, it has reached a pure gas. You don't want liquefied refrigerant entering the return side of the compressor, as this may damage or destroy the compressor. So that ends the cycle and it starts back over, and we have this sequence of gas to liquid, liquid to gas with the refrigerant, and then we have the cycle of heat rejection initially and then heat absorption finally. So this is the whole premise of heat removal rather than so-called cooling.